Okay, Assalamualaikum warahmatullahi wabarakatuh. For this one, we will cover chapter 3 of our course statics, which will be dealing with the equilibrium of a particle. Right. So depending on the time, we will cover the 3.1 to 3.3 slides, which deals with two-dimensional problems, and then if time permits, we'll straightway go into 3.4, where we deal with 3D problem, three-dimensional problem. Right. So yeah, by now you should have already covered all of chapter 2, where we already know how to get each forces into Cartesian vector form, right? So those are among the things that we will apply here when we deal with equilibrium problems, right? You should know how to express each forces already into Cartesian vector form, and that also include all the possibility of trigonometry, right? Resolving forces, projection angles, coordinate direction angles, and also using unit vector or position vector to get the force into Cartesian vector form, right? We have three possibilities that we have covered in chapter 2, where how to express each force into Cartesian vector form. Either you have or you are given projection angle, coordinate direction angle, or coordinates, right? Three inputs which we have covered already in chapter 2, how to use to get the Cartesian vector form of any forces. We will have to use all those into this chapter, especially in 3D, right? So hopefully by now you have covered all of the material for chapter 2, and we'll go straight into chapter 3 inshallah. So based on the slides, alright, so we begin with equilibrium of a particle, free body diagram, and coplanar force system. Now, in this chapter, all of the body is still a particle, right? It's not an object with a dimension like this. It's a particle, it's a point, right? So that's where it is much simpler than any object like this, right? Because if it's a particle, every force acting on the particle actually got inside, and we don't have any distances between forces, right? Which means everything is simple, straightway it should be, right? Now okay, so okay, let's go to the coplanar force system, right? Section 3.3, right? So if you see the slide, it actually gives an example of a 2D coplanar system. Coplanar meaning everything in the stream plane, meaning it's two-dimensional, and that's 2D, where you have a cable at the ring there, or a point, and then you have a weight. Right? That's an example of 2D problem. And for particle, right? Where is the particle? It's at point A there, right? Now, so first thing first is a free body diagram, right? So for any equilibrium problem, you have to start with the free body diagram, right? In the chapter 2, we don't have any equilibrium yet, right? It's just resultant force. You have to be able to differentiate between resultant force and equilibrium. Resultant force meaning you have several force. What is the resultant, right? When you add all the force together. But equilibrium meaning when you have multiple force at a body, when it's equilibrium, then it's not moving. It doesn't, meaning summation of all forces equal to 0. That is equilibrium, right? So it's two different things. When you deal with equilibrium, you have to draw free body diagram. When you have dealing with chapter 2, resultant force, there's no such thing as free body diagram there, right? So starting from this chapter, you have to deal with free body diagram a lot. So make sure you know how to draw free body diagram, right? So what is it? So we have free body diagram, right? Free body diagram. So what is it? Fundamentally, it should be a diagram, right? So when you draw, it should resemble a form of diagram, right? It's not some, abstract sketch that no one can understand. It should be a proper diagram. That's number one. Number two, it should be specific for any given or specified body that either the question wants or you have determined, right? So meaning when you look at the diagram, we should be clear which body are we considering or we are talking about, right? So, for example, if we have multiple objects interact with each other, if we are considering this body or this body, the diagram will be of that body or of that body, right? So it should be clear, and then it should be free, right? When we say it should be free, meaning that let's say if we have a ground, right? A floor, a ground, and then we have an object here, right? A box on the ground. So when you say, okay, I want to draw the free body diagram, so of this body, of this box here. So okay, this is my body. So this will be my body, for example, right? And then it should be free, meaning that it should be free from any other things, any other object, any other body, etc. Right? So here we have the box and the floor. When we say this is the free body diagram of the box, it should be free from the floor. If you still draw the floor, that is not a free body diagram because it's not free from the floor, if you understand, right? So if we have a table, for example, a table, right? And then a box on top of the table, right? So if I say I want to draw a free body diagram of the box, so the box should be only the box without the table, without the floor. If that's free body diagram. If I want to say I want to draw the free body diagram of the table, it should be only of the table, not the box and not the floor, right? That is what it means by free, right? It's free from anything else, right? If you have any other object that it interact with, that should not be in the diagram if it is a free body diagram. Unless, okay, for example, if you say no, the body is table plus box, then you can have, okay, if this is my body, then it should be free from the floor, right? And this is one body, right? So that is what we will be dealing with in chapter 4 or 5 later on, because in this chapter we don't have this possibility yet, because our body will be a particle, right? A particle, meaning that, for example, if I have something here, and then there's a cable, there, there's a cable there, there's a weight there. So in this chapter, our body is still a particle, meaning that, for example, this one, right? This is the body. So the body will be just that, without any cable, without any box, without any ceiling or wall, etc. Right? So that is what it means by free body diagram. Make sure you understand that, because when you still draw the floor, for example, then this is not a free body diagram, and then your mark of a free body diagram, you will lose it, right? So that is the importance of knowing what is a free body diagram and drawing it properly, right? So make sure you understand that. Alright, so that's what it is, right? So why do we need this one? Because in the end, any of our calculation for equilibrium problem should be based on your free body diagram. So without any free body diagram, there's no basis of your equation that you use, right? And hence it's a problematic, right? Because when we want to see whether that equation is correct or not, it is based on a certain free body diagram. Without the free body diagram, we do not know whether the equation is correct or not, right? And as I mentioned in the first class, make sure, because in this course of statics, one of the learning outcome is drawing the free body diagram. You know how to draw the free body diagram. Even if you do the calculation, the equation and the calculation correctly, the final answer is correct, but the free body diagram is missing, you're still not showing that you have learned how to draw the free body diagram, and hence you will lose your mark there significantly. So make sure you know how to draw the free body diagram correctly. Alright. Right, so we go to the slide of how to draw the free body diagram. So it says that first imagine the particle to be isolated and kept free from its surroundings. So that in the slide you can see the diagram there of the question, right? For example, we have a floor here, not floor, we have a wall to the rim here, the ceiling there, and then we have a certain width. So the first step is draw the body itself, in this case the particle, free from anything else. So this is my body, for example, right? So that's the body. That's the first step. Second, show all of the forces acting on your body, on the body, right? So in this case, we have a cable here that is pulling in that direction, so we have a force here. We have a force pulling it that way, and then we have, for example, the weight here pulling it down, right? Show all the forces, right? And then you have to specify all the forces, right? Okay, I'm already showing it straight away, right? So you have to label the forces if it is unknown, but if the number is known, you have to put it. For example, here 9.81 Newton. For example, if it's already given as 10 kilogram, for example, right? So the value, if you know the value have to be there in your free body diagram. If you do not know, you have to label somewhere label the forces accordingly, right? And then is this complete? No, you have to also specify the direction. So whatever theta here is, if you know the value, for example, you know the value. If you do not, you have to put theta, etc. Right? So the label must be there, right? So only that, of course, normally, okay, for a full complete free body diagram, the axis also should be there, right? And here, several things. Make sure when you draw something, the meaning is correct, right? So when you draw forces, you have the arrow here, right? And make sure you draw it correctly, right? So it is something like this, not something like this. I don't understand what this is, so do not draw like this. So this is what we mean by force. And then for axis here, do not put arrow here, because then it's confusing which one is force, which one is an axis. So the axis is drawn without any arrow, right? So make sure when you draw, the meaning is accurate and people can understand which is what, right? So those are important for your marks and also for people to understand properly, right? So this is basically a free body diagram, example free body diagram of that example. Okay, hope that is clear. Right? If you are missing anything, because if you miss the angle, then something is not properly defined, you miss some marks. If you do not put your number, even if the question knows the number, they give you the number, you miss some marks, you lose some marks. If you do not label, you lose some marks, right? And why is this important? Because when you do the equation after this, in your equation you have F1, F2, W or whatever, it should be clear where or what that means, right? Or where it comes from. So in the equation, if you say F1 and then you see here F1, then at least it's clear what you mean, from where it is, right? When you don't label it and suddenly you pop up F1 or something, it's not clear what that means. So that is the problem if you do not have a free body diagram, or if your free body diagram is missing some key elements or information, right? And of course afterwards is the equation of equilibrium, where you have summation of forces equal to 0. Of course this is in vector, or basically you have summation of fx to 0 and summation of fy equal to 0 in terms of scalar, right? Now if you write something like this, then I will give you this. Why? You should know why by now, right? Because this is wrong. If you add all of the forces in the magnitude, right? If you have the 10 times 9.81 and whatever value here and whatever value here, if you add them, it will not be 0. It will be some value there, right? Mostly positive, right? Because a number plus a number plus a number will be another number. It will not be 0. Right? It will only be 0 if it is a vector, for example, because in terms of vector, you have ij for two dimensional, and it will have its direction, positive or negative, right? If you do this one also, you will have, for example, positive to the right or positive upwards. So when you have downwards, oops, sorry, it becomes negative, right? So that is important, right? If you write like this, the meaning is wrong. Magnitude, additional magnitude will not be 0, right? Make sure you understand that. Do not be surprised if you lose marks because you do something like this, because the meaning is wrong. Alright? So, and the rest is just summation of the equation of equilibrium. And I believe you have learned this already, right? Summation of forces, summation of fx equal to 0, summation of fy equal to 0 for 2-dimensional, right? And it's stated there in the slide, right? When you have two equations, summation of fx equal to 0, summation of fy equal to 0, the maximum number of unknown that you can solve is 2, right? So if you draw your free body diagram and the unknown is more than 2, either you cannot solve it. If unknown is 3 or more, you cannot solve it actually, right? Those two equations, or something is missing, meaning something is actually known from the question. The question already gives the value, right? So you have to put the value there. Only 2 of the forces or angle or whatever should be unknown. And then the slide actually solved the problem, and I believe by now you should already know how to solve equation of equilibriums, and we will try some example after this. But for this one, you can just follow the slide, and I think it's straightforward to be understood, right? Now, in terms of the when we draw free body diagram, is of a certain object, and there are various objects that you should be able to understand. One is cable. Now, it's not in this slide, but from the understanding of the problem just now, for example, right? If we have something like this, and then width here, right? Now, when you draw the body and you draw the force like this, for example, right? What does it mean? It means that the object itself is being pulled in that direction, meaning there's a force pulling it down. If you draw something like this, the arrow upwards, what does it mean? It means something push it upwards, right? So that's why we have, in this case, the weight will obviously pull it down, so this will be correct, this will be wrong, right? Make sure you understand the meaning. You cannot just simply assume the direction. The direction is understood to be going down, meaning the force is pulling the particle or the ring here down. So you should have to draw it down. Now, what is the meaning of this one? Right? The meaning is, this cable, the understanding is this cable is pulling it to the left. Right? To the left, right? From the side of it pulling to the left. Right? What if I draw it to the right? Is it okay if I draw force from this cable to the right? Is it logical? By now you should be able to understand already, because you are taking engineering course, you should be able to understand basic fundamental understanding of objects, right? Now, if you have a cable or rope, right, it is impossible, meaning if you have a rope, it is only possible to pull it. You cannot push something with a rope, right? Because it have to be, how to say, what's the word? It has to be, meaning a rope, okay, this is a rigid object, right? With a rigid object, I can push something, right? I can push it. But if this is actually a rope, I don't have an example, right? For example, or something like this, right? I cannot, if it's tied here, right? For example, okay, this one, right? I can possibly push, pull. This is possible, right? But I cannot push this. It will never happen, right? So when you draw something like this, the meaning is the cable or the rope is pushing this particle, which is illogical, which means you will get a wrong for your free body diagram because it doesn't make sense. as an engineering student, you cannot fundamentally draw something like that. It doesn't make sense, right? Similarly here, the cable can only pull it. It can never push it, right? So the meaning is very important. You have to understand the meaning of your arrow, what it means, and is it logical in the real world, right? So make sure you understand this, right? So there are other objects also. That's cable, right? So cable can only pull. In this chapter, because we are dealing with a particle, we rarely see any like a member like this, right? Because if it's something like, okay, let's say if it's something like this, right? Okay, so this is a cable, but this is something rigid like this, right? It's a member rigid like this with a pin there, right? So in this case, we will cover this in the later chapter, right? But just to explain, in this case, this can only be tension and this can only be tension, right? Meaning it's pulling, right? For this one, this member, because of it is rigid, it can possibly be push wing. It can be pulling, it can be pushing, right? Because it's rigid, it's possible, right? So that will make it more complex, and that is for later chapter, inshallah, right? So just to give you some sort of idea what is the difference between cable and something rigid like that, okay? But fortunately in this chapter 3 we will not deal with this one yet, I think. Now there are other objects also. One is simple spring. You see the slide, there's a spring there, and I believe you have covered about spring before, right? From matriculation or foundation or school, right? So but the idea is simple, right? So if you have a spring, so we know that if it is being elongated by this S, right, meaning this is the original length, for example this is the original length, this is the new length, for example. So it elongates by that much, so the force is Ks, right? K is the spring constant, right? Normally the question will give to you, unless the question want you to calculate that one, then it will give something else and you have to calculate K, for example, right? But F, the force from the spring, will be spring constant multiplied by this elongation, right? Now that is the value, but how is it how to say, meaning how to draw the force, right? Okay, by the way, before we move further, if this is the case, then you know S here is L minus original length, right? L minus LO, for example, right? Because some question will give you original length, some question will give you extension, etc. So you have to understand what is the information given by the question, right? Now, so if we have, for example, question just now like what we have just now, but instead of a cable, it's also a spring there, and then we have a weight there, right? For example. Now, if you draw a free body diagram of this, right? A free body diagram of that. Now, this will be just to the left, as we understand before. It's a cable; it will pull in this direction, right? And then the weight here will be obviously also because it's being pulled downwards, right? But for this spring, right? For that spring, logically it depends on whether it is an extended or is compressed, because it is possible also, if this is the original length, when you compress, right, where this is the new L and it is being compressed by this much, right? So if we have a compression, then the force is different, right? In this case, logically, if the original length is here, right, let's say this is the original length and then this is S, for example. Is it clear from the diagram? Right, meaning that it's being extended, the logical meaning is, if you extend a spring, right, if you extend, it want to go back to its original length, right? The spring, if you extend, it want to go back. If you compress, it want to go back, right? So in this case, it want to go back there, right? Meaning the spring want to go back to its original position, so it will pull it in that direction. Why? Because it want to this direction, right? It want to go back to its original position, so it will pull this point to that direction, right? So that's the meaning, right? If, for example, let's say, if originally there's a spring like this, right? And then we put something on it so that it becomes something like this, right? Where it actually go down for a bit, right? In this case, the spring want to go back to its original position, right? From here, it want to go back here, right? It want to go back there. So if you draw the free body diagram of the box, the spring actually will push the box up, right? So the drawing should be like this. If you draw like this, it means that the spring pull it down, which is in this case wrong, because we know the spring originally here, it goes down and then it want to push you up, right? So if we have another case, for example, if we have from the ceiling, you have the spring originally is here, and then when you put a box, if you touch a box here, there's a box there. That's it. So let's say it's originally here LO, but now it becomes here L, where you have this extension S, right? So in this case, what will the spring react? It want to go back up to its original position, right? So if you draw a free body diagram, the spring will pull it up because it want to go back up to the original position, the original length, right? So that's the meaning of why you draw upwards like this, or why you draw upwards like this. It's not upwards actually, it's either it's pushing or pulling, right? So it depends on the original position of the spring and the final position, whether it want to go back or it want to go back, right? So you have to understand those things, right? So the arrow is important. If you draw like this, for this case, if you draw downwards, that is wrong because the spring is not pushing it down, right? That's wrong, right? So hopefully you understand. Now, because this is the drawing in the free body diagram, the F equal to Ks is the value, right? So for example, this is F equal to Ks, whatever S here, right? And whatever K here. In this case, F here is equal to Ks, right? This S here, for example. Similarly here, F here equal to Ks, but this K and this is S, right? So F equal to Ks is just the value, but the way you draw in the free body diagram is also very important, and you have to understand what's the original position, what's the final position, and what's the tendency. Alright, that's spring. The next one is pulley, right? So in the slide you have cable and pulley. Alright, so in the slide actually, if you see something like this, right? If you have a pulley, let's say you have it hanging there, and then you have a cable here and cable here, right? I'm straightway drawing the arrow, right? In the actual question later on we will have an example. For example, it can be something like this. There's a weight there, and for example there's a spring there, and whatever, right? It can be anything, right? But for understanding, we'll just go here first, right? So the question gives you, for example, this is T1, this is T2, whatever angle here, right? So how is T1 related to T2? So that's the fundamental question. Of course, if you see the slide, you already know what's the relationship, right? But I hope you actually can understand what it means, right? Now, in this case, you have to understand that this and this, or this one and this one, is actually the same cable. It's the same rope, right? So the fundamental understanding is this. When you have the same cable, even though it goes across a pulley, right? For example, it goes across a pulley, it goes across the pulley, etc. It's still the same cable, and in one cable, you cannot have different value, right? It should be having the same value throughout. Then it will be in tension, right? Otherwise, right? Something like this, right? So throughout this, or for example, if this is pulley, right? So this one and this one should have the same value, right? Otherwise, it will be it's not logical, right? It should be the same value. So meaning that T1 equal to T2, regardless of the angle, it doesn't matter. For example, if I have, so you have something like this, going here, going here, going here, going here, going here, and there's a box there, for example, right? And going here, and there's a box there, right? For example, there's a lot of pulley there, for example. But this is the same cable, right? For example, cable going here, 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 right? So, if you draw the free body diagram, for example, if you draw a free body diagram here, there will be a force here, right? This T, right? And if I draw a free body diagram here, it will be something like that. Right? If I draw a free body diagram, okay, let's say if I draw a free body diagram of this pulley here, it will be something like this. Okay, this is a bit complicated, but if I draw, it will be something like this. Okay, this one we haven't covered yet, but I'm just showing, right? But anyway, so what is important is this is all the same cable. Meaning inside here it should be T, inside here it should be T, inside here it should be T, 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 right? So that one, right? So if we have something like this, then this tension here should be the same as tension here, or the force here should be the same as force here. Right. Now, why use T instead of F? Because when you have a cable or rope, we call it a tension, right? Because it's always in tension. So sometimes we use T, right? If you want to use F, it's more general for force, but it means the same thing in this case, right? So the meaning is it will be the same. The tension should be the same, right? And if you have something like this, for example, right? For example, right? If I have another cable here, or whatever there, right? For example, right? For example, right? So if you have something like this, if you draw the free body diagram and I consider this is my body, the diagram will be something like this, right? And there's a tension here, and force there, right? If I consider this as T, let's say this is F, right? Then actually if you do summation of Fy equal to 0, you can get F, if you give outputs as positive, F minus T equal to 0, so F equal to 2T, right? Which is logical because this force should be equal to this T plus this T, or 2T, right? So that's an example of free body diagram also, but this one is later because in this chapter our free body diagram is always a particle, right? Alright, so for this particular thing, we don't normally do in this chapter, we don't actually draw or need to draw this free body diagram or this free body diagram, etc. because we're covering pulley is just so that you understand that if you have a force here, it should be the same thing here, right? So you don't need to draw all this free body diagram here, just know T equal to T here, for example, right? So that's the important point here. Alright, in this case, the slide also cover smooth contact, right? And in terms of smooth contact, basically you'll have a normal reaction, right? For example, the easiest one is if you have let's say if you have ground here and then you have a sphere object there, when you draw a free body diagram of that thing, then this is the normal reaction, right? So it's perpendicular to the ground, so that's normal, right? So if it's something, the ground something like this, then if you draw the free body diagram, it will be that way, or it will be something like that. Right. Of course, free body diagram, the ground should not be there. The ground should not be there. If you still draw like this, even though if you draw the force, this is not free body diagram because this is not free. The ground is still there. It should be free from the surrounding. Alright, so those are some elements that you need to understand because it will affect how you draw the free body diagram. Alright, so example 1. So we go to this example 1. Alright, let's go. So we have something like this. So we have a box here. So this is to something there where it gives you the angle of 3, 4, 5, and then here we'll have something here with the angle of 30 degrees, right? And it gives you the point labels of A, B, C, and then D, and then this is 550 Newton of weight. Alright, and the question says what is the force in rope AB and AC? So the question asks what is the force here and the force here, right? So how do we do this? First, do you understand the question? The question gives you this diagram, this picture. We have the box of the weight there. We have 2 cables, and you need to find the force in the cable. Right, so the first thing first is to draw the free body diagram. So this is the body, the particle, free from anything, right? So that's the body, that's the first step, to draw free body diagram, and then draw the forces. So basically the weight obviously will pull it down. This is a cable, so obviously it will pull it that way. This one will pull it that way also, right? And then you have to label it. In this case, the value is known, and make sure you take note of the unit. This is already 550 Newton. It's already in Newton. Do not multiply by 9.81 because it's already in Newton, right? Because some students actually did that mistake in the final, which is a sad thing, right? Sad mistake to do, right? Because you lose mark on something like this. So make sure you just see, okay, if it's in kilogram, you multiply by gravity. If it's already Newton, that's fine. Okay, let's label this FEC here, FEB here. That's unknown, and that's what we need in the final answer for this question. What is left is the angle. So we have 3, 4, 5, and then we have 30 degrees there, right? And of course we have x-axis, y-axis there. Alright, so that will be the complete free body diagram, right? So what do you do next? Basically, equation of equilibrium, right? So we'll have summation of fx equal to 0. Let's take to the right as positive. So you'll have FAC. By now you should know how to use this triangle stick already. So in this case, 4/5, and then minus, because it's to the left, f a b cos 30 degrees equal to 0. Right. Now, normally in terms of the mark distribution of the solution, each of the steps have its own mark. There will be mark here, there will be mark here. If you straightaway write this equation without this original equation of equilibrium, you'll miss the mark there, because that is an important step of the calculation, of the analysis, right? You start with, okay, I understand it's in equilibrium, so summation of f must be 0, or summation of fx must be 0. You state that, and then this here is summation of fx equal to 0, right? Another thing is, sometimes some students actually jump into, when you, for example, from here you can get FAC 4/5, you bring it there equal to FAB cos 30, right? Now, this is the original equation of equilibrium of f, summation of fx equal to 0. This is the manifestation of this, meaning that summation of fx is this minus this. That's summation of fx. It should be equal to 0, and this is already the calculation steps. You have bring something there, etc. Now, if you skip this one, you miss some mark. If you skip this one, you miss some mark also, right? Because that's the original summation of forces equal to 0, right? So you should not skip all of these steps in the exam if you want to score all the marks, right? Now, this is for fx. So you have also summation of fy equal to 0. Let's say you take upwards as positive. So here you have, okay, let's start here just to be consistent. Okay, so here you have FAC 3/5, and then plus FAB sine 30 degrees, and then minus 550 equal to 0, right? All of this summation of Fy equal to 0, right? So before you start calculating further, that statement should be there also. Do not skip steps, because each step will give you the marks. Now, in this case, obviously it will be a simultaneous equation, right? So however you want to solve simultaneous equation, you can. For example, if you do this one, FAC equal to 5/4 FAB cos 30, and then you put this FAC into this FAC, so you get all of this here, blah blah blah, and then calculate. So that's, for example, how you solve, one of the way how you solve simultaneous equation. So you just solve and then you get the answer, right? So that is just mathematics. After that, it's just mathematics to solving simultaneous equation. Now, if you see the final exam question, and I have put some on iTaklim for your reference, right, from previous exam. In the cover page, it will say that you have to show all the steps, including simultaneous equation. If you see the slide, they have the equation, and then suddenly say solving, you get the answer. Because, and nowadays also you have your calculator that can solve simultaneous equation, right? But for the calculation step and for your mark, we have some marks there. If you suddenly use your calculator and jump to the answer, you'll miss some marks in the calculation of solving simultaneous equation, right? So that's how normally we do. So make sure you understand that. Right? You just have to show the simultaneous equation calculation, right? To show you know how to do the math also. Alright, hopefully that's understood. So we have another example, example 2 here, right? So I erase this first. Example 2. So there's something where we have a wall here, and then to the particle, and then we have the weight here, and then it goes here, and there's a pulley there, so another weight there, whereas this pulley is attach that, right? Something like that, right? You can see your slides, right? So the information given is this is 30 degrees, this is A, this is B, this is C, and then 40 kilogram, and then this is D, this is E. Right. So the question says the mass of the cylinder C is 40 kilogram. And geometry as shown. Find the tension in cable DE. Okay, so what is FDE? Tension in cable EA, this one, FEA, and EB. So this one, what is force EB? Right. So that's the question. What is the force in this cable, and this cable? Right. So hopefully you understand the question. Alright, so now you have to imagine how to solve this one, right? The question is clear, hopefully, and how to solve is by first drawing the free body diagram and solve equation of equilibrium, right? So free body diagram, okay, in this, because currently we are covering chapter 3, it's obvious that it's a particle, right? So you know we draw a free body diagram of this one, right? But when you go into the final, we have covered a lot of chapter, so you should be able to decipher, okay, this question, to solve it, we just need a particle, because in some other chapter we need other things also, right, which is not a particle. Now, so if you have force here, and okay, make sure you understand also the difference between this and this. This is that like a ring where the cable is attached like that, right? So everything coincides at one point. It is different than pulley when the rope actually goes around the wheel, right? So this is two different things, right? So this is a particle, this is different, right? You cannot draw a free body diagram of a particle here. It will not work, right? All right. So the body is point E, right? This point E here, right? Now, so in terms of this cable, what we will draw is to the left, right? So we have FDE, right? And going down here, we have FEA. We do not know the value at this current point because the question do not give any value here. So we know that it's FEA. And here, so it will be something like this, right? FEB, right? However, as we mentioned before, there can only be two unknown in one question for 2D because we have only two equations later on. So something must be known, and we know, okay, when this is given, so this tension is known, right? Which is basically 40 times 9.81 Newton. And that should be the same here, right? So actually FEP is known to be 40 times 8.91 Newton. It's known from here, right? So that one is solved already, right? Because the question actually asks what is FEDE, EA, EB, so this one is known from the beginning. And we have also the angle of 30 degrees. Alright, and also the X and Y axis. Okay, so that's the free body diagram. How to solve this one? Okay, first, before how to solve, hopefully it is understood, right? Why is this like this, right? Do not, meaning when we draw a free body diagram, we are focusing on the body itself. In this case, this particle, and we draw all the force acting on that particle. So this cable is here. This cable is here. This cable is there, right? We do not care of what is on the other side. For example, on the other side of this cable is this box, but that's not matter, right? Because we just care about, okay, it's this cable, right? Because the one that is attached to the point is the cable. Similarly here, it's the cable, so it's straightway to that direction. Cable must be in tension, right? So we don't care whether there's a pulley, etc., etc. This information is only need to be understood to see that this tension should be the same as this tension. It should not affect how we draw here. Is it going there? That is because of cable must be there, right? Should not be confused. All right. So we can draw, we can do the equation of equilibrium. For example, we start with summation of fx equal to 0. Let's say to the right is positive, so we have that FEB 40, 9.81 cos 30 degrees. That is that one. Minus FDE equal to 0. Then obviously you can calculate FDE equal to something straight away, right? So you solve that one. And then you have also summation of FY equal to 0, upwards as positive, for example. So here you have 40, 9.81 sine 30 degrees, so say upward. And then this one is downward, minus FEA equal to 0, so FEA equal to something there. Right, you can substitute. In this case, it becomes short because there's no simultaneous equation, because this is horizontal, this is vertical, so it doesn't coincide, it doesn't have any angle, so you do not have to solve by using simultaneous equation. Right. So sometimes the length of the question can depend on aspects like that. In this case, for example, no, this is the same. Right. So because the unknown is just in one axis, so it's straight away. Alright, so that's how we solve. We have covered 2 examples. That's how we solve 2-dimensional problem of equilibrium problem. Right. So you have the concept quiz. Do cover some of the concept quiz to just test whether you understand or not. If something that you don't understand, please discuss among you or ask me either in the class or in the comment there. We will try to address, inshallah. Right. Okay, we have another problem. Group problem solving. Right. I will erase this first. So here we have something like that, something like that, something like that. Something like that, right? So we have A, B, C, A, B, C, D, E, F, and then we have the angle of 50 degrees here, 45 degrees here, 3, 4, 5. Alright, so the question gives you this diagram here, and the question actually gives this is 20 kilogram, the lamp. Is it the lamp? Yeah, the lamp, 20 kilogram. So find the force in each cable. So the question just says, find the force in each cable. How many cables do we have? So we have, for example, here, FDE, here FCD, here FEC, here FBC, right? Or if you want to include this one, is also okay, FDE, right? But of course, from here, you should know already this value can be calculated straight away from here before even doing any free body diagram, right? Because it's simply just because of this weight, 20 times 9.81 meter, right? Alright, so we basically have 4 unknowns, right? Can you solve it? We mentioned earlier, for a free body diagram of 2D, you have only 2 equations that you can use on the free body diagram, so you have only 2 unknowns that is be able to be solved, right? But here, because we can see that we can draw free body diagram here and also here, so we can have 2 free body diagram. For each we have 2 equations, so for each we can solve 2 unknowns, so here we can solve 4 unknowns, right? Okay, that's number 1. So you have 2 free body diagram to do, right? So the question is, when we have question like this, is where to start, because you can start at this free body diagram or you can start at the free body diagram, right? So before you start anything, you should be able to think first which option you should take, right? So the question is, should I start with this one, free body diagram of point C, right? That's the question. Now you should be able to, just from visually seeing it, you should be able to tell that if I draw from the beginning, if I draw a free body diagram of point C, how many unknown will I have in the free body diagram? It will be 1, 2, 3, right? So you have 3 unknown, you have only 2 equations, you cannot solve, right? So do not start there. If you go to point D, how many, when you draw the free body diagram, how many unknown? This one is known already, this one is unknown. So you have 2 unknown you can actually solve, right? So start there. So with that, we draw the free body diagram of point D. This point. So basically we'll have this weight going down, which is 20 times 9.81 Newton. And then you have FDE with angle of 30 degrees. And then you have FCD horizontally like that, right? That will be your free body diagram, of course with the X and Y axis also. So from here, what can we do? We can solve both of these, right? So in this case, it's easier to start with vertical, right? Because we have a vertical value here. So we do summation of Fy equal to 0, going upwards, positive. So we have FDE sine 30 minus, sorry, this is wrong, right? This is 20, right? Why is it 29? It's 20 then. So minus 20, 9.81 equal to 0. From here, you can solve FDE equal to 1, right? Because there's only one unknown here, you can solve straight away. You can get the value. You can see the slide for the value. So for here, I'm not wasting my time to calculate, so I just show the step, right? So from here, you can calculate FDE, right? So when you do the next equation of equilibrium, is the summation of Fx, Fx equal to 0, to the right as positive. So basically you have FDE, which is known here, FDE cos 30. So whatever value here you can put, minus FCD equal to 0. Then you can calculate straight away FCD equal to something, right? So right there you have already solved for FDE and FCD. After you solve that one, then obviously this become known and known, and you can go for this free body diagram, you can solve for this one and this one, right? So next we draw free body diagram of Okay, I might just write FBD, right? Of point C. Free body diagram of point C. So you have point here, point C, and then you have force there, which is FEC, and then you have force here, FBC, and then you have here FCD, which the value is already known, right? So you should already, meaning whatever value here, you should already start, you should already put it here, right? Because you know already the value, so that is not. What else? So this one is 3, 4, 5, and this one should be 45 degrees. And you should know this one because this is what do you call this? And this is 45, this should be 45, right? So having this established, so you can do summation of fx equal to 0. Let's take positive to the right. Obviously, in this case, you will have to do by simultaneous equation. Why? Because these two forces have x component and also y component, right? So you'll have basically FCD, the value itself, you know already the value, so you just plug in there. So minus FEC, what is it? 3/5, right? And then minus FBC, cos 45 degrees, cos 45 degrees equal to 0. Right? So that's one equation. And then upward positive for summation of Fy equal to 0. So basically you have FEC 4/5 minus FBC sine 45 degrees equal to 0. Right? So you can solve this simultaneously and then you can answer what is FEC and what is FBC. Right? So that is just mathematical calculation. Right? So in the end you have solved 1, 2, 3, 4. And also this one from the beginning, right? Right? So that's how you solve an example of question like this, right? So in the exam, it can possibly be that you have multiple free body diagram that you have to draw, right? For example, if the question is something like how to, whatever the case is, I don't know. But if you have 1, 2, 3, or how many particles that you have to consider, the step is just the same, right? You draw free body diagram of one, solve, and then get the value, draw another one, solve, get the value, draw another one, right? So the important thing is you know where to start, which free body diagram should you do first. So normally you just follow where the value is. Here there's no value given, here we have value given. So normally that is where you can solve and then go to the next point, right? So that's for the answer. For the value, you can see the slide. We have the slide, right? Alright, so that's the end actually for the slide 3.1 until 3.3. Alright, that's the end of the slide. After this we will have another recording for 3.4 because this is all still two-dimensional, right? We can go for three-dimensional in this next recording, inshallah. So yeah, hopefully you understand. Do try some examples, do try some problems to see whether you can draw the free body diagram and then solve the equation of equilibrium, right? So with that, I'll end first this recording for two-dimensional. Wallahu a'lam. Subhanakallahumma wa bihamdik asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Wassalamualaikum warahmatullahi wabarakatuh.